wasn't planning to do a regular Optimosophy video anytime soon, let alone any one of those randy types episode, which that seems it will be. As I'm more focused these days in some exciting projects, Opti news coming soon about that, and released enough previous episode already. I want to take a break from it till I prepare for my next purely algorithmical examples and avoid a bit the randy types. However, something happened. I was trying some random stuff on my own that led me to search for some specific modern PC optimizations, and I found some nice articles, but there was something in one of these articles. Were some comments that triggered me again. Had me ranting alone in the air and wanting to make another Optimosophy just for this rant, just for showing you something. And it led me thinking of a curious concept. I like to call it the programmer's evasion. It's not even certain what evasion means. Evasion from what? I'm not sure. I'm still exploring this idea. I might have been inspired by the title from a random philosophical document, and now also a small book. A document I have accidentally read many years ago, maybe more than 10 years ago, with the title The Human Evasion. It was written by Celia Green, and it was like a philosophical treatise. I mean, it's hard to read even today. If I try to read it, I'm not sure if I understand. But it was describing something in the human psychology, a tendency to avoid certain higher level subjects, and insisting on focusing on the human affairs. And it's like if you have big questions about life, about the universe, about... It could relate to our niche hobbies too. Some people will always be like, why are you even spending time on that? And that's pointless. You shouldn't even be doing it to begin. You shouldn't even be allowed to be doing it. We shouldn't be that's it's like it's criminal to even do it. And why don't you spend time on the human affairs? You know, just like the rest of us. But it's like the people saying that, criticizing, they didn't like something was scaring them by the fact that you would just want to delve into subjects that are a bit unorthodox or a bit too far out there. And I'm not sure I understand the whole concept or why it happens, why humans do that. And some chapters on the book I was reading fast, but it was that concept that got me interested. And there was also something witty about her writing, and a sense that she was talking about some human tendencies that are universal, even question what we consider as rational. You know, with the irrational being, when you are not, for people, the irrational is that you are focusing on unorthodox and out of the box kind of thought, and you are not focusing on the mainstream, on human affairs, but your mind goes a bit too far, and that you shouldn't even do that to begin. That's the irrational thing for a lot of people. Like, rational is their side, you know, like, I can't explain. I'm not even sure where to place it, and I'm killing its idea, so I should stop here about this thing. But anyway, it goes that title, The Human Evasion, and something maybe similar that made me call this episode, and the whole concept, the programmer's evasion. And it's that sense of human psychology creating narratives to secretly and unwillingly avoid things in a way that you don't see it, You think you are rational for avoiding this thing, and you are rational for telling everyone else that they shouldn't even start with this thing. And that thing might be related with certain tendencies and things that are promoted or in the programming field, either promoted or other things that they want to push you away from these things. Like, this is the only way to program, and these are some things that we shouldn't do anymore. We should never do this or that anymore. You should program the new way, you should never do things the way we did. But it's not like the excuse is we're trying to be professionals or we are the better programmers here, so there is some evolution. But it's so dogmatic, and I think there is something greater underlying here. It's not just the excuse we make about programming, it's something in the psychology. It's the tendency to avoid some things and make a rationalization of why we should avoid it. Why I should avoid it, that person telling me, and you should avoid it, and everybody. It's almost a crime that we even do some of the old stuff. And I can't explain it much, so I will just run. And forgive me that if it's disjointed, but I think now the essence of my videos will be this. It might be long, it might be disjointed, but this is something that I think about our field and about the magic of programming and how it's lost, and this is something that I want to express through Optimosophy. Besides algorithms and some clever idea, I want to express the different schools of thinking in programming, this programming evasion, the tendencies in the field. And even if this is going to be like 80% randy video, but as it still has to do about programming, I will at least start the beginning showing you a bit of code and showing you a bit, very briefly, some of the things I was trying, where I was trying old school unorthodox tricks in a modern PC and how they fail. We will see how this thing fail in modern PCs and whether it's necessary. At that point I realized I should have to look at some modern things. One thing is parallelism, and the other thing is interesting, is the vectorization intrinsics. If you don't want the compiler to optimize your vector, something I have never done before. This is something for a future episode in exploration. If in modern PCs with millions of pixels, if I was to code the same software rendering effects, if those intrinsic would give great speed up that even the compiler cannot figure most time. I mean, the compilers have some optimizations for SSE and AVX and all that new stuff I never touched before, but I think that's the way to go if you want to optimize further for modern PCs. Even though in modern PCs you can write some mediocre optimized thing and you still be fast. We will see about that. And I'll show you that the old methods don't work anymore and they are so silly and unnecessary. But it's fine if someone tries, in my opinion. It's fine if you try the stupidest thing. And I'm even going to do it for trolling. Not for trolling sense, but for... not trolling, like... I'm gonna do it, man. I'm gonna write a code that has 1 million go-tos. I have an idea for a code with... I want to see if I can break the compiler. And what is the limit of the go-to labels. But that's for another show. But here I'm gonna show you some other unorthodox thing I did. And then that thing led me to start searching articles on some different technologies. And I was puzzled that even with newer technologies that are relevant, some people had that programmer's evasion was creeping in some of these comments. And in a way that is not like I don't want to do that, but you shouldn't do it either. Anyway, there is something actually fascinating about the whole thing. Both the power of human ingenuity behind all these optimizing tricks, but also the psychological avoidance that it triggers. So first I will start with some experiment I was doing that are not related to the rest of the rant on the video, rather than they made me wonder about some new, more modern things I have to try on the PC, and led me to some article with some comments that triggered that thought. So it's irrelevant, but I want to start a bit. I want to show you some silly things, so that it's part of some episode to show the unorthodox code, even if it fails, and exactly to learn that some things fail. Some theoretical optimizing ideas might be counterproductive, I should say. Especially in modern PC, that things are different. You don't even need to optimize. For example, here, this is my PC SDL for software rendering, SDL2. And for now I'm running in 720p. And I wanted to try one of the old effects I was talking. I was talking about this tunnel, not exactly, it's a different shape now, but the static mapping tunnel in one of my episodes. And I wanted to try, what if you did it on a modern PC and try to do what the Commodore did? My first attempt was to not do what the Commodore do, but do it more formally. Like every pixel on the screen will look backwards to the texture mapping, U and V coordinate. So the first attempt was the more basic one, and I have a relatively small texture, and I think init new method, extract new method. Oh my god. fx init. That's the old method. Okay, dst. So in this one, I have these texture offsets. It is an array screen width by screen height for every and it gives back an offset to the texture. So I calculate some kind of, it's not a tunnel, it's like a sphere mapping thing with a warp on the outside, U and V, and I just store the V multiplied by the texture width plus U. I don't even store the U and V separately. I store the total offset to the texture. And so that's the basic one. Render classic. That's what we call now. And so now the destination, I'm going through every pixel, and the source, that big array goes back to the texture. It's so simple as that. And now the texture is a 32 by 32 thing, and because it's a small one, I have a move texture for all three examples that will, it scrolls by an offset x, offset y, and it does a modulo with the texture width and height. It gets it's just doing XOR texture, something very simple. And it writes, this points to the texture, the destination. It redraws a scrolled XOR texture on the 32 by 32 static texture so that the whole thing scrolls, while this is a static mapping in this way. So let's run it. And you see, oh wait a minute, I remember a bigger flavor. Okay, I press start debugging, or start without debugging, Control F5. Yeah, that's how I remember. It was bigger before, but anyway, it depends. Okay, oh, I know why. Because I'm capturing. The frame rate I noticed was very... Yeah, it's hard to see it now, man. Because I'm capturing in real time. But we have to see it roughly. And here I have some averaging. So as this goes on, because even the original was very variable on the PC, the system is working in the background. Sometimes you get 900 frames, sometimes 1000, 1200. I was hitting 1200. This is how fast this effect can be in software rendering those resolutions if the algorithm is so seamless, a direct mapping. But that's not the point, is to try the rest. So at least here you see an average after some time, because it will accumulate the total number of frames and divide by the total time elapsed. So at least if you want to get a more accurate, you can get the total average, about 960, okay. And so I thought, a render new method. And this method, it uses another array, source occurrence. This one I don't allocate, I define it here. Texture width by texture height. Ah, yeah. And in this one, I'm trying to do this method that people do on the Commodore, the forward rendering instead of the reverse rendering, where you find every texel of a texture, the various position where it's rendered. So you read once the texture and you store it in several arbitrary positions in the screen. So it's the opposite. The previous method, as much pixel you had on the screen, you did one read for those. If you had 1 million pixels, you did 1 million reads, 1 million writes. But this technique, if your texture is 32 by 32, you will do 1000 reads and 1 million writes. And that was great on the Commodore 64. And even other computers, especially those who didn't have a cache. And so, out of curiosity, I was like, what if I tried this on PC? And let's see what... Init new method. In Sorda, I'm trying to get some indices, occurrence. This is a summation. How many times each texel appears on the screen. So that I have an index that points to the next, in a big buffer, to the next. If the first texel appears 1000 screens, then it has a sum of 1000. So if you jump 1000, you go to a position for the second and the other texel. And at that place later, you have, based on this offset, you have the RAM offset. It's hard to describe. It doesn't matter. I use those arrays to do the new method. And see, the old method was in the inner loop was one now. The new method, the inner loop is still. I'm just, I'm going through the texture size, text width by text height. So I'm going through each individual pixel. I'm getting a count. How many times this texel of the texture, this appears, this pixel on the bitmap on the texture appears on the screen after we map it. If it appears no times, we continue to the next. Else, you read the texture only once. Yeah, you do a loop in the count and destination, that's the screen video RAM. And these are the offsets. These are the offsets. This point, this point, this point, this point, this point, random points, not lines. Like this point, this point, this point. See. So I tried that. I say, what happened? And I was kinda expected that it would be slower. Here is something that will be faster on the Commodore, and it's pointless to do on the PC. Let's see. It works, but it's slower. And my guess is the cache. In the first example, you do as many pixels there are in 720, like 700,000 pixels. So many reads from the texture and so many writes, and it's the simplest possible. But because the texture is small, it fits in the cache, of course. Even if it was bigger, even if you try with a bigger texture, still faster. And that's why 624, now that I'm capturing, was the first example was doing 960. In this, if you look on the average after a long time, 620. I have different numbers here. So I was doing 1960, 624. So we have proven that something that seems would be faster because of modern PC and caching. Here I'm doing more. I'm reading from the source pointer with all the offsets. I'm reading from the destination. I'm doing two reads that are big. Actually, I'm only reading this. This one is writing. And I read the texture once outside. And this one reads the texture all the time. But it is faster. The naive method is faster than the, let's say, Commodore 64 method and or other. So we have proven that some ideas are not as... They might be good on old computers, but on PC you have to work in a different way. But it's good, in my opinion, it's good to try. It's good to see, it's good to try silly things. And the reason is cache. This one is, okay, it's doing more reads, we avoid the reads. Not really. The texture is small, it fits in cache in the first read. Then it's just writing. And I tried with bigger texture. The texture has to be very big, and still it would be faster. You see some drops with bigger textures, but still faster. And here is the wildest thing. The wildest thing I have tried, and to finish this coding section that led me to other things, is render new method extreme. That's the funniest thing. I like to do things that will terrify programmers because I wanted to do it, okay? Because that's unorthodox programming. I use this one, which I have commented. I used it one to extract unroll beast codes. What if you did what the Commodore did with those tuners? Unrolled every pixel. But the Commodore might have a tunnel that is 64 by 64 in size. Okay, with a 16 by 16 texture. Okay, and that would fit in like 50K or something. That's the funny thing. But here, if you do unroll every pixel, you are going to create a beast. And I have created the beast called Lele, a 20 megabyte beast, which we can see here. So I generated this code. So it reads texture at place 0. And see, it has the destination just like the Commodore, but unroll on different places. It throws pixels on different places. It's silly. I would never write a real code like this. It just... And thankfully Visual Studio didn't explode. Then it finishes with a position, it reads texture 1 and does the same. Destination in the video plus different position and so on. And it finishes with, oh my god, this is too many because it's the color 0, I think. It's not 0. I have a pixel. Maybe that's not it. 1023. It's the last pixel. It's the same. Look at this beast, and Visual Studio didn't explode. I was planning to do it for a 1080p or 4K resolution, but I was like, nah, maybe another time. I want to make really the Cobalt explode, and I have an idea for another effect to try like this, but I will never try this again. Because it's silly. You don't even need the clever short Commodore method. You know, you do the naive simple method, it's going to be the fastest. But let's see how I'm calling that one now. Let's see how that performs. And it works. Oh, in combined generates code. It didn't take ages, thankfully. But it's nice to try. It's nice that I'm showing you that, because nobody tries even simpler stuff. It's interesting to try something extraordinary that doesn't make sense anymore and see how it behaves. And prove that, yeah, don't do some of these old school tricks. And my opinion is, if I tell you don't do this, do it. Explore it yourself if you please. If you please trying things that other people told you, don't try it because I tried it and that doesn't work, so you don't need to try it. No, you will try it. You will try it if you want to, if you insist. Because someone telling you, don't try it because I try it and I've proven that it doesn't work, so nobody else should try it after me. No, I don't agree with that. And it takes forever. I don't remember it taking so much. It takes forever. Sorry, I drink a bit of quinine. Because I can wait. Oh yeah, finally. Oh, it works. That monstrosity worked. But you see already the frame rate. You have this enormous thing in cache. You see it. $280 frames. You see the difference. Those numbers was also when I wasn't recording. But now I'm recording, so it's a bit slower. And here is a thing that you notice, and let's put the original version without any tricks. Besides that tunnel mapping. That gives you another perspective that even the bad method for PC would yield almost 300 frames per second. Even the bad method, I could have not tried this one. I could have gone directly for the extreme method, thinking it's the most optimized shit ever. I could have made 300 frames and see, my monstrosity is great because it's optimized. And then someone would do the classic and say, what? No, man. I wrote a clean code, the smallest code ever, with these precalcs, and it's much better than your monstrosity. Okay. You don't even need to do the second option. But all three options are crazy. So much that you could have missed that a naive approach is much faster, like almost 1,000. And I'm talking about this because here is another rant. People underestimate how fast the PCs are. Okay. I'm doing software rendering in 720p. I know that some people will go on 720p and write an unoptimized effect. They will even use floating point and mathematics everywhere. I mean, maybe floating points alone are fast, but if you use trigonometric function, if you use sine and cosine per pixel, or a tan or a sqrt, like I use here for the precalculation, if I did the precalculation in real time, okay, which means if I goes to call this, that's going to be naive, of course. That's another thing. Where is the init? Okay, I hope it works like it. If I goes to call this to calculate the mathematics every frame, and that's not the right thing because I'm also doing the other stuff. But let's see. If I was like, why are you doing lookup tables, man? Even with the first method. PCs are fast. You just write everything with floating point, it's going to be fast. You get a much less frame rate. Still, you could get 70 frames, okay. 83 average. If I recalculate everything with the square root for that one and the floating points, although I shouldn't also render the thing, but that's a crude example. So, imagine someone would do the floating point approach, get 70 frames and think, I'm a god, 720p software rendering, man. And it's so fast. I'm the god of optimization. Software rendering is slow. I was expecting to get 5 frames per second. People would think that. People would think if you go to 720, if you go to 1080p, people would think it's software rendering, man. I'm not supposed to get over 30 frames per second. Oh no. Ah no, it doesn't generate the code with it. No, this is, oh god. It's not filling the screen because it's... I have to make it full screen to see all of it, but still, 1080p effect, software rendering, and I'm getting almost 300 frames, 270, 280. Okay, with a naive method. And it's going to be worse with the other method. And someone could say, okay, now I'm calling this one. Let's calculate per pixel. I'm doing that again, I've done it before. Oh, I'm a god, man! In 1080p software rendering, I'm doing 35 frames. Or 40. Look how it breaks. I'm a god, man. What do you expect, man? Software rendering. I'm repeating myself. Why am I saying that? Because there is a sense that, man, that computers are slow. There is a sense that I go and create a Gouraud shading cube 3D or a rotozoomer or a plasma on my 286 and I can get 17 frames per second for the rotozoomer, 50 frames per second for the Gouraud shading, 30-40 frames per second for the plasma. And people think 286, I remember, was horrible. You can't even get 1 frame per second. People think if I go on a 286, I might write a 2D star scroller and that's it. Okay, I will move 100 points and that's it. They underestimate the power. And they would write something with mathematics and get, because they underestimate the power, they think, okay, man, it's 1080, okay, it's a million pixel. It's 2 million pixel actually. And they would think, whoa, I must have written very fast code so that I get 40 frames. What do you expect? 60 frames, 100 frames? Are you crazy? You cannot get 100 frames. And then you get 300 frames. Now you get more because it's not complete. Anyway, you get the point. A 1080p effect, it's a very simple. You can do plasma and rotozoom. If you start doing filters and other stuff, then things will slow down. I was going to try it for 4K, but I need to put it full screen. And I'm capturing. So, the point I want to make here, I was thinking about that. I was thinking that I'm still compiling x86. Okay, it's x64. Okay. How does it behave in? Is it faster, slower? I did 960 on this resolution. Maybe it's a bit better with a 64-bit. Yeah, it could be, yeah. Yeah. But okay. The point I want to make, some of the code is a remnant of the 386. I'm not utilizing the newest capability of those processors. The parallelism and the vectorization, for example. And I was very interested about the vectorization. Okay. Here's where it hit. So I was thinking, okay, if that tunnel effect runs 300 frames on 1080, and I wanted to make a software render demo, and why do when you can use the GPU and achieve greater speeds? Well, let's say I wanted to optimize some pure CPU effect. Okay. Even if I stick with x86 or x64, I mean, regular PC instructions, whatever the compiler, and even whatever the compiler creates without even writing a line of assembly. If I was to stick to that, it will still be enough to do very fast things, and you don't see it. Sometimes you see very slow things. Okay, the demo scene, it was in the past that they did on the Pentium 3. That they did demos at 800 by 600, like the non-stop Ibiza experience by Orange, for example. I used to mock this demo because it was running slow on my Pentium 1 at the time, but it's doing some in high resolution. At the end, it's doing bilinear texture filtering with transparencies. It's doing a lot of hard stuff for 800 by 600 resolution, I think. And then it dropped. Then okay, nobody was doing software rendering demos on PC, but some later demos I have seen was in 320 by 200, and they were struggling. It was maybe 480p, and it wasn't the fastest thing. You could see some frames dropping. I saw one on 720p. I guess okay, the coder was learning. I don't want to blame anyone. And it was showing something running at 10-15 frames per second. Something like I can easily take my code and it will do 200 frames per second. Even my 3D code, because that was a 3D torch or something, and I was like, I guess it was just, so you can fit that thing, the most run-of-the-mill code, it will run. You will get 15 frames, and you will think it's heroic, because software render is not supposed to be fast at those resolutions. But no, as I told you, There is great potential. But okay, here is the point. At that point I thought, so that I don't go into other... if it's pointless to do that stuff, if it's pointless to do this stuff, but this is okay if a minimal code and some pre-calculation can produce this. And you can maybe do this in real time with calculating things with floating point in a grid and interpolating, like some demos did later. You don't necessarily need to do lookup tables. You can work on that one in other ways. There are other ways of thinking around this. If you want to do it real time and change its shape on the real time, because this is not changing its shape, obviously. So I thought, okay, these things can go fast no matter what. And maybe I should try some harder effects, like some filters, some box Gaussian filter and radial blur. I have tried some of these effects. These are indeed heavier. I think I did a box filter on 720p and I was doing 60 frames per second, 30 or 60. It wasn't. It was like 40, 50. So that's when it hit me that I should look not just on parallelization, but on simmed intrinsics. I heard about simmed intrinsics. And you might say, you don't need to. The compiler has some option to optimize for simmed, but I don't think it might optimize very trivial things like adding vectors or some dot product or something. But you could write your pixel-based effect with the simmed intrinsics working together in chunks, in RGB channel chunks, doing 4 pixels at once. And you could make things, especially the heavy filter effects on 1080p resolution or even 4K. You could do some real-time demo with heavy stuff on high resolution, something we haven't seen from the demo scene. We see this slow res stuff going slow, and I'm like... so if regular compilations with x86 is not enough for you, this is the way to go. And here is the point. This is where I started reading this article, which is a nice article. I don't have any complaint about the article. This is where my rant starts. This is where I noticed again this programming evasion from some comments. Okay, and the original author replies very well at these comments. And also this simmed intrinsics is something I want to look in the future and try to write some heavy software effects and try then to optimize them with simmed intrinsics. They seem awkward at first, but they are very interesting because you could handle many pixels at once, many color channels at once, and all that stuff. And you can, but you have to specifically, in my opinion, the more complex algorithms have to specifically be written for that. And maybe I'm mistaken. I don't think the compiler, if you write something very specialized, that's what the author has described. You can optimize and get like 3-4 times the speed. From 3 to 12, he says. And that's the way, if you have some heavy software effect that did 30 frames per second, that's the way you could get above 60. And way more. If you are on a dead end. And this is the modern thing. If on modern PC I stop doing this monstrosity, which I never did in my modern project, I never needed, and it's a bit stupid for a modern PC. Or even try to make some new method thing in the hopes that it will be faster and then it will get slower. If I'm stuck with the x86, that's the way to go, and that's the way to use the modern PC. So I said, great. Yes, I should be looking at this in the future. Okay, let's go to the rant because I'm repeating myself. It describes some things well. It's a nice tutorial for starters. It does some tests. It shows some speeds, it has some easy algorithm, grayscale and dot product and blah blah. Someone said, okay, but dot product, the compiler can do some SSE optimization on that. Sure. 5 to 12 times faster. This is how you get some big differences. We are underutilizing the PCs. In this one, I'm underutilizing the PCs and still get 900 frames or 300 worse. Or I'm getting 300 frames on the 1080 for 2 million pixels. This is how fast the PCs are. And we think it's slow because we write a bad algorithm and you get 5 frames per second and you think, yeah man, of course, software rendering is slow. What did you expect? No. Here's some other methods I want to see. And he also does a bit more complex algorithm with fluid filling. He has also some GitHub for that. So it's a nice introduction, or maybe like, yeah, man, simmed intrinsics. That's a good way to go. To radically improve your performance. Not 30%, not 10%, not 30%, like 5 times, 4 times, 10 times, 3 times. Okay. And here we come to the rant. And I made the mistake to scroll down in the comments. That's okay, they talk about the code. C#. I'm looking for it. This guy here. Huh? I have yet to find a compiler that doesn't optimize the dot product to use simmed, latency hiding included. I don't think disregarding all the effort put into auto vectorization, probably by not enabling the relevant compiler switches, is fair. There is some limited use for simmed intrinsic and critical section, but usually, and by that I mean 99% of cases, writing clear code will enable the compiler to optimize just fine. Just write your code different and the compiler will optimize. Here is the kind of evasion, like, why do you need to do that? The compiler does it for you. All these engineers work on this compiler and you think you are smart. Okay, I may be paraphrasing and I'm putting more words to this guy. It's not the one that surprised me, but here is a bit sense of some evasion. Some why should we have to do that stuff? There are experts doing that for us. And he says, I have yet to find the author of the article, unless he says they don't do that. Just look at the performance tables in that article, and you see manual vectorized version is multiple times faster even on GCC. It doesn't do it perfectly. And even if it does, that's the point. Even if it does, even if you have a case study that proves me, hey, look, here the compiler did it better than you. Okay. It's unpredictable. And when you tell me, hey, but in my case, it doesn't seem so. It seems that when I manually optimize the simmed instruction, what he says, I can get better speeds. I can overcome. And the answer would be like, oh, if you write clear code, the compiler will do it better than you. Okay, rearrange your code, write your code different till you get it. You know, play with the unpredictable compiler and you will get it. Okay, he's like, okay, yeah, am I wrong? Maybe you're right on that. But there is, he said that it once shows I tried some other flag, some other compiler, and finally got it. Finally got the result that proved my point that you should not do it on your own. You should always rely on the compiler. Day that you even tried. And he says, it once again, so it's like, it once again shows, this is like, as we all know, you don't need to optimize anymore. As we all know, there is little need for low-level fielding these days. And this is called low-level fielding because it's some intrinsics. Because it's not some high-level readable that non-geeks will understand. He didn't even write assembly, and he is using a modern thing. The SIMD architecture is the most modern stuff you will ever... I'm not even using. I'm in the past here by compiling for regular x86. I'm not utilizing some modern stuff in the processor that could. In this case, I don't need because it's already too fast. But if I write heavier algorithm for software rendering, which might be moot because you can use the GPU with shaders. But fine. But these are modern. There are people. The same things are modern. They are not. When did they become old school? So that the person is like, "What are you doing? You don't need to low-level fiddle." Okay. So what if I wrote assembly? Would I be prehistoric? So that's what surprised me. This is a modern article about modern things. There are modern engineers using those SIMD things. The CIMD is a new thing. And it shouldn't be a new thing that you just set the flag in the compiler and be done with it. It's something that you should be able to use. Especially if for a specific algorithm, not for the simple examples. You can grab the CPU from its pins and make it your own, you know. I'm surprised that even for modern stuff, because it looks like assembly. It's the assembly instruction, but in some macro format. It's called intrinsics, and I need to read more about it. And I'm surprised, like, oh no, you don't need to even do that, the modern thing. 2 out of 3 examples in the articles, dot product and brightness are very simple. And then even those examples can improve. And you could use some compiler flags and rewrite the code, which means rearrange so that the automatic vectorizer will do the right thing. You know what that is? It's like the compiler is a child. I will tell you this metaphor I have thought many times. You have to do some heavy work. You do it yourself and someone says, hey, why do you do this work? People used to do it in the past. You can put the compiler, but is this clueless child to do the work for you? And then it's a misbehaving child. It's an unpredictable child, the compiler, that will do. You will give some high-level commands, and it will do something that might not be optimal. And you are like, what does the compiler do? Rearrange, they say. If you write it right, but what does right mean? People think, oh no, if the code is no, because it's unpredictable, you will, okay, let's rearrange my high level commands and then observe the child again. Oh, now the child does it a bit better, but not too much. Rearrange the stuff, I don't know. Write things a bit different, and maybe the little child will understand how to do it. So let's spend all the time. Here is the programming evasion. You're putting the time, you're putting the effort to do it yourself, and someone says, you don't need to put the time anymore. This is a thing of the past. Put the child. You put the child, it doesn't do it right, and says, but it doesn't do it right. I didn't spend the time and effort, but it's worse. And he says, but if you tell the child to do it different, you might eventually get it. So now I will spend the time and effort to fight with the compiler to convince the child to do things exactly the way I thought it in the first place. So I will spend the time and effort in something I could have spent the time and effort myself, where I have full control. Okay, and you will tell me you don't need to do it, but the automatic tool doesn't do it. Oh, you can look. I have proven you. If I do this and that, maybe I can convince the automatic thing to do it faster. Okay, so that person who is trying to evade, that's the programmer's evasion. There is something psychological that says we have to prove that you don't have to do it. We have to fight the compiler so that I convince you that you should not do it yourself. But the automatic thing doesn't do it always right. Oh, that's because you didn't fiddle with the automatic thing enough till you get the result that I want to do, the convincing that you don't need to do it. It's like that. It's like I have to go out of my way to convince you that eventually the automatic tool will do it for you better than you. And why do you even try to do it yourself? And there is another reason, because the child that you give the word, the automatic tool, the little AI thing, okay, AI, you could think it as an AI that is, it doesn't have the human spirit and the ingenuity to do it absolutely good. It does something good, and it will change. You will vendor lock in a specific compiler, specific version of the compiler. What if the new GCC changes the optimizer and something that you fiddled, something that you tweaked so that it gives you the better results, so that you avoid writing it yourself, because you should not, we live in the current year, we live in 2022, and you should not be doing low-level fiddling these days. You should not be doing low-level fiddling, but you should do excessive fiddling with the compiler so that it gives you the result that I can use to prove to you that you shouldn't be wasting your time in the first place. So you should waste the time for the first place till you get it right, so that you have a code that the compiler happens to. I'm repeating myself, but do you get the concept? You should not waste your time. But if it's slow, it means that you didn't waste your time enough to convince the compiler to write the optimal code for you, when you could have wasted your time to write the optimal code yourself, to do manual fiddling, as he says, low-level fiddling. And he responds well that if you waste your time, what if the compiler changes? What if there is a new compiler that breaks the fiddling? It's not going to break your simmed instruction, simmed intrinsic writing, the specific thing you will write. It's going to generate a bit different code with SS simmed flags and so on. And even ignoring multiple compilers, it does not mean there is little need for intrinsic. As he says, look, I have a more complex. You are talking about the dot product and bright, which are simple. I have the vectorized version of my float fill algorithm. Okay, I have the float fill algorithm. There are more complex instructions, and those are the real. It's not the dot product you want to. There are a lot of rendering algorithms. Even someone mentioned not just graphics algorithms, but in the AI space today, simmed instructions and simmed intrinsics, even manual writing them, could massively improve some algorithm in machine learning, in AI, and some other fields. Even if you do it wrong, you will still get some speed. It's not like 10%, 20, it's 4 times, 8 times. If you do it badly, maybe it's two times or 3 times. If you don't know what you're doing, you still get a lot of speed. He's explaining here. You have to be very specific where you. People think you are just going to throw some complex algorithm and the compiler sim will do its magic. Well, you have to be very specific here with your data structures, and you design the sim because it's packets of data, and maybe you give it different packets of data in a way that is more optimal. No amount of automatic vectorization is gonna help with that. Here he says some compilers never touch memory layout or data structure. They treat it as given. Adjust data structure for sim friendliness is often an important step. The compiler is agnostic of what you're trying to do. Okay. It takes an input and gives back an output. You have specific algorithms and you can design them around those simmed instructions or whatever. Or even before simmed, you would design around in a way that the compiler would not necessarily give the best. Also, C-lang outperforms this. So he's like, yeah, I found C-lang. Yeah, I did that on C-lang and with all this flag and did everything for me. And here is the God block proven. One less optimized. This is the evasion. It's like something inside you says, I don't want to. I want to avoid things of the past. There are various reasons about that. Why? And I want to get my short exam. Let's see, we don't need to optimize anymore. We have to leave this in the bin of history and lock the bin and throw the key away. I have heard that. That's the same with other programming things, old school C, C++ stuff. Now we have the new school C++. We have to. There is this kind of mentality, and I call it evasion because I don't know what it is, and I have many theories. And maybe one theory is not an evasion, but maybe one theory is that there is this sense that if I follow the modern stuff and disapprove the older stuff, and this is not old. The sim is not even old. It just looks like old. It looks like old because it's not some high-level readable code, and you have to know your packets, what kind of bytes they have, or words, or whatever in this vectorize. You have to know. You have to be very careful and know what are these. I think they used to be 64-bit. Now they're 128, 256 in AVX, maybe 512 bits. Imagine how many packets you can have. You can do 8 pixels at one, 16 pixels at one. you know. And these are modern stuff. And the guy too early says, no, we should not do it. They do it for us. I prove this for you. Here is the thing. You don't need to. I proved my point. And there is a bit of a talk that what about portability if a computer has AVX1 and AVX2? Yeah, this guy has all modern PC 64-bit PC processor will have an SSU1 or 2. I mean, you could detect this and have older versions of the algorithm. I mean, you are optimized specific algorithms. Okay. It's not that bad. It's not like your entire project is. You can have your entire project written in C++, whatever, and have a specific algorithm that is heavy optimized with that stuff. Why not? Why is there this evasion? Like, oh, I don't want to go back to the dreadful 90s where we have to hand optimize assembly. It's not even us. I mean, it's assembly instruction, but it's through those intrinsics. It's a mix of C and the SSE instructions. And here is the thing. Here is the anonymous, and thank God he's anonymous, because I don't feel well by putting those names out. I mean, okay, the other guy, he's trying to be a quote professional programmer and so on, because that's the idea. If you use the modern stuff and avoid the things that look old school, that's the thing. The SSE, they look old school. It's either evasion or like putting you in a different category of a programmer. Like I'm the more professional programmer because I know that these things are bad and should be avoided. There is this idea always, these things should be avoided. We should not have this thing. We should nuke it out of the planet. It's not like this is a tool. And why not? And it's a modern tool. This is what broke me. It's like, even the modern thing. What if I wrote in pure C and with inline assembly, or what if I wrote everything in assembly and some projects still use? It wouldn't be popular. It would be prehistoric for these people. When the modern stuff, when there is an evasion for the modern stuff because it reminds them the old school. But these are things that some probably heavy imaging and other software might be using them. And this is the thing, the post that broke me. It's not like, oh, you don't need to do that, or if it goes like, fine, but I don't want to do that. If you want to do that, fine. I don't think it's necessary for me to use those intrinsics. But if you want to use them, go. No, you shouldn't. You are not a good programmer. Look what this guy says. Any half respectable programmer, the dogma, okay. The dogma and maybe an evasion. The evasion where you get angry and you are like, I don't want to have to do anything with this, and you shouldn't have to do either. So I'm going to call you. If you have a curiosity on this sim stuff, no. That's what this guy says and annoys me. Any half respectable programmer will understand that it's bad practice to use intrinsic in application level code. Really? This is a matter that now look now the antithesis here. Look the contradiction. He said not exactly. I will explain the contradiction. Maybe it's not now yet. This is a matter. So do the intrinsics have any use? This is a matter that belongs to library and compiler authors. To say the least, this post that Konstantin wrote is of no use. Because 99 of the users who should use this probably have more knowledge about this topic that you can gather here. It's an ancient part of the C language with more than enough papers available online. Those intrinsics are CPU dependent, hard to produce, especially the latest. It should not be consumed by the end user. So this guy is not like, I don't think I'll use that Wi-Fi. It's like, you shouldn't. Any person who does it is not a respectable programmer. Is a bad programmer. We should call you out. We will discourage you. We will discourage you to explore even the new things that look low level. And he says to this guy, you shouldn't even have written this article. It's unacceptable in the whole programming field to write this article. That's what he says. Okay, and the Trump guy says, and any fully respectable programmer will understand that some intrinsics are very useful and that performance matters. They are just functions after all. Well said, but he's saying 99% of the users who will use it will not read your article. They will already have the knowledge. And I guess those people will be library and compiler authors only. And the thing is, it doesn't make sense that because this is a thing of experts that no regular programmer will use, you shouldn't even have written the article. Because I might be a young person. I'm not a young person. I'm not a young person now, but a young person, inspiring new programmer who is interested in performance, will come here and read that and say, what is this? I haven't worked with that one. And will start learning. And that young generation, the new generation, at least those few who are still interested for performance, will learn something from that and will experiment and will be the next people, will be the future coder that would be the library and compiler programmers. Okay. But you say you shouldn't write. Nobody should. This knowledge should be esoteric, should be forbidden. That's what you are saying. Or maybe you think 99, no, it says 99% will not come in Stack Overflow to read this. Like it's some esoteric, super crazy, no, like a young person cannot come read some stuff and try something and learn something and start a career in low-level compiler programming and be a superstar or something. If it should only be used in the library compiler author, because I don't believe that. Because I believe you can use them in your special project. Maybe you write an image processing tool or something. And there are some heavy operations on Pixar. Or maybe some AI. I think AI and machine learning, those things might be very useful. Or other stuff, and you are experimenting. You are a young person. Why do you want to discourage? Why do you want this shouldn't be here? Because it will make the user programmer use that stuff and it's wrong and it's bad and you shouldn't be. I will discourage people experimenting with modern stuff. These are modern stuff. This is not writing old school assembly. This is not doing this monstrosity. Which I would support people trying the monstrosities, experimenting, trying the things that will make you not respectable programmer. That's the post that broke me. And also, that's the programmer's evasion. Like, yay, we found one less reason to optimize by hand. We should be finding more reasons to disprove the need to optimize by hand. Why don't you say, Why is it? Does it try? There is a trend that this has to become a industry standard. Dogmatic opinions that you should not do that. You should leave it to the experts. I hear people. I hear people. In the big organizations, they're the expert. The people who make the Boost library, they're the expert. Man, not only they made a much more readable and maintainable library, it's going to be faster. Why would you rewrite algorithms when you have everything in Boost? I have found in my work at least 2 algorithms that we wrote faster versions. No, one algorithm I wrote something faster because it was a specific thing for a problem. And initially, someone would say, "Why do you want to write it yourself? Boost has a function about that." And I tried the Boost function, but for the specific thing we wanted to do, tailored to the thing we wanted to do, and not the generic function that the Boost has. It was like many times faster. Okay, from something taking 5 seconds, it was few milliseconds. And the other thing we didn't write, it was a CRC algorithm. And there was someone who wrote a CRC algorithm that was like several times faster than the one in Boost. Because maybe Boost did something. That's the thing. These people will say, why write that? You are going to write something that is in Boost and you are going to write a slower version. It's like the experts have figured that for you and you should not have to do that. It's not like don't bother, or it's not like if you want to bother, but I'm not going. It's you shouldn't bother either, and it's a disgrace if you even bother. If you even bother to learn the lower level ways, it's a disgrace. This is what these people say. It's a disgrace. I will call you a bad programmer. I will call the whole world bad programmer, and this article shouldn't have been written. And should not be consumed by the end user. This is the meaning of esoteric knowledge. I have heard some. I have heard this thing in the past when there were some cults, and they said esoteric knowledge. No, esoteric is a Greek esoterikos, and it means like internal knowledge. And I never understood why it was called esoteric. And I think I read somewhere that some of these cults, it was like there was another word, a sacred knowledge. It was like a knowledge that should not be given to the public. It was like this knowledge is dangerous to the public. Yeah, you can write software that will blow up, according to. Because like we should not democratize this knowledge. You should have the experts, the compiler and library experts. They will only teach this on university. There won't be articles in Stack Overflow for the hobby programmer to learn. Okay, for the inspiring programmer to inspire. Okay, to try things. With some real interest, with some real passion. You should not be. It's like some kind of elite who is like, we should all be user programmers. You should not even inspire someone reading this article to try. That person who reads the article might be a future compiler programmer, for all I know. Why don't you let it like, okay, that article is not for me, but maybe it's for others. And Constantine here replies, well, I'm surprised he's so calm at replying, which I like. Should not be consumed by the end users are different. If you don't need them, don't use them. There are many people working on video games and on gaming, 3D graphics, CAD/CAM, video processing, image processing, those things. You can make things much faster with heavy image processing and heavy video processing. Complex embedded software, similar things that need to compute stuff on large amount of data as fast as possible. Yeah, okay, you can find a library that does what you want, but it's not always the case. A good argumentation, and it's what we do here with graphics programming and other stuff. Here he says the addressings are the same across all compiler. You will have at least SSC1 and SSC2. Maybe you target the low side. Maybe you do detect and have a fallback. Modern operating system cannot install or boot without SSC2. I didn't exactly knew that, but and these comments are okay. They are just discussing. And you know, those comments are good because they are discussing the concept. They're discussing the subject of the article. The subject of the article was not whether we should use it or not. It was like, hey, you can try that too. Okay, you can improve the performance if that's your thing. But we have, I guess, 2 people only. But you see the programming evasion. That's the meaning of the end of my video. You see the programming evasion of we shouldn't have to do that. We shouldn't have as a programming field. So neither should you. You shouldn't have even write this article. They will not, those who write compilers, they study that in universities. They are the expert. You should rely on the expert. And there you even write this article. It's esoteric knowledge. It shouldn't consumed by this end user. And if you play with these things, you are not a respectable programmer. You are a bad programmer. I will discourage you. And that's the general feeling that is in the field. Like, there is this feeling. There are 2 theories. One theory is the programming invasion. It's like these people are afraid to go. What if things go back and what if I have to do that in my future job? What if someone says you have to code like this because we want to use that, we want to get some performance? And I hate the old ways of programming, or I learned to hate the old programming because someone told me they are bad. They are so bad, they should be deleted from history. Or my other theory is that there's some psychological thing that if I cling to the modern and the future stuff and I discourage the old stuff, I will virtue signal that I'm the better programmer, the more professional programmer, that understands that these things are things of the past, and clinging to things of the past are bad, so I must be good for disregarding the things of the past and sticking to the latest new thing. Which latest new thing? Tomorrow some expert will come and say that latest new thing is not the latest new thing anymore, it's the old thing. And as a good boy, as a respectable programmer that virtue signals my professionalness and the unprofessionalness of the others, I will cling to the new thing and disregard the previous new thing as a thing of the past that nobody else should play with, and this guy should have never even written the article. That's the programming invasion. Whether it's because of fear or because of thinking you are a more modern professional programmer, and this is how you signalize it to the programming world. And that's what I wanted to say. That's what made me think about this thing. That there is something, and maybe always, creeping like that. That it doesn't even make programming that art where you would be inspired to explore that stuff. You would be inspired to explore these things that they are not all. These things are new. Because the intrinsics makes the code look very, and it has to do with assembly stacks, and it makes look very old school. You just don't want to bother, but you want that neither anyone else bothers. And that bothers me. Anyway, guys, that was a randy Optimosophy. And hopefully the next Optimosophy, which will take time, will focus on specific algorithms. Less randy and more showing the good magic and the inspiring magic. Bye!